Okay, now let's try some where we go from rectangular to polar coordinates. And as we were discussing at the end of the last video, there's more than one way of writing polar coordinates for the same point. So we're going to do this more than one way for each rectangular coordinate point. So we're looking at 1 square root of 3, which would be this point here, -1 negative root 3, which would be the blue point down here, the point 0, 1, the point 3, -3, the point -5, 2, and the point 0, 0. Now, here are the answers, but let's talk about how we get them. For the point 1 square root of 3, if I were converting this by hand, r would be the square root of x squared plus y squared. So it would be the square root of 1 plus 3, the square root of 4, which is 2. And to find theta, I notice that y over x is the square root of 3 over 1. So theta would be an angle whose tangent is the square root of 3 over 1, like the arctangent of that. And that would be 60 degrees in degrees, or pi over 3 in radians. So we could write this point as 2 60 degrees, or 2 pi over 3. But we could also take that angle and add or subtract 360 from it if we're in degrees, or 2 pi if we're in radians. Or we could make the 2 into a -2 and just add or subtract 180 degrees, or pi radian. So that's what I've done here. +2, 60 degrees is the same as -2, 240 degrees. For the point -1 negative root 3, r is still the square root of x squared plus y squared, still gives you 2. And this is a point in quadrant 3. So we could say it's the angle 240 degrees, or 4 pi over 3. That would be equivalent to -120 degrees, or -2 pi over 3. Or we could say, well, r is -2 and theta is 60 degrees. Facing 60 degrees and taking 2 steps backwards takes you to the same place as facing 240 degrees and taking 2 steps forwards. The point 0, 1, remember where that was, just right here on the y-axis, is where r is 1, because we're 1 unit away from the pole, and theta is 90 degrees, or pi over 2. We could also add 360 degrees to that, or subtract 360, or if we're in radians, add 2 pi, or subtract 2 pi, or add or subtract any whole number multiple of 2 pi. Or we could say r is -1 and theta is 270 degrees. So that would be like if we were facing straight down, but taking 1 step backwards. The point 3, -3 has r equal to the square root of 9 plus 9, square root of 18, which is 3 times the square root of 2, or approximately 4.24 in decimal. And the angle, and notice this is in quadrant 4, where x is positive and y is negative, down here. We can call that angle -45 degrees, so 45 degrees this way, or we could say it is positive 315 degrees. And we could also write those in radians. We could also write a version of this where r is negative. For -5, 2, actually, let's see what the calculator gives us for this one. Right now, my calculator is in degree mode. Let's leave it there for now and see what we get when we go to the angle menu and put in R to P R, that is rectangular to polar, and give me the R coordinate for the point -5, 2. It gave me 5.385 and so on. Now that comes from the square root of 25 plus 4, the square root of 29, which is 5.385 and so on. And then for the angle, the theta coordinate, go back to that angle menu, select number 6, rectangular to polar theta, and again put in -5, 2. And I was in degree mode and it gave me approximately 158.2 degrees. Of course, if you wanted the radians, you could be in radians mode and ask it. And what about the point 0, 0? Well, I didn't put down anything, but the point whose rectangular coordinates are 0, 0, that is the origin or the pole. So for polar coordinates, we can write 0 anything. We can write 0, 0, we can write 0 pi, 0 pi over 2, 0 whatever. Now let's do some equations, some simple polar coordinate equations and inequalities. In what region of the plane is r theta so that r is equal to 4? That is, think of all the points that have their r coordinate equal to 4, and then theta can be anything. Remember, r represents your distance from the pole. So if we're 4 units away from the pole in any direction, that puts us on this circle here. So all the points on this circle of radius 4 centered at the pole are all the points that have their r coordinate equal to 4, and then theta can be whatever it wants to be. In what region of the plane is r theta so that r is greater than 4? So now we're talking about your distance from the pole being greater than 4. You're more than 4 units away from the pole. So now we're out here, all the points outside that radius 4 circle. In what region of the plane is r theta so that theta equals pi over 3? Remember what theta is. That's the direction, the angle. If we're at an angle of pi over 3, we're going this way. And if r can be anything, 0 or 1 or 2 or 3 or however far we want to get from the pole, we're just going in this direction. That gives us this line. And if r can be anything, that means r could be negative. And for negative r's, we get this part of the line, points that are down here, where theta is pi over 3 and r is -1 or -2 or -3. In what region of the plane is r theta so that theta is between pi over 2 and pi? Pi over 2 would be this way, like straight up. And if r could be negative, that also gets us points straight down, all the way along the y-axis. Where theta is pi would be out along here, out along the negative x-axis. And if r could be negative, that includes the positive x-axis. So theta would be between pi over 2 and pi when we are in quadrant 2. If we just allow r to be positive, we just get quadrant 2. But if we also allow r to be negative, we also get points down here in quadrant 4. So these are the points that have polar coordinates r theta, where theta is somewhere between pi over 2 and pi. So these have been pretty simple, basic polar coordinate equations and inequalities. What gets interesting is when we get to some somewhat more complicated polar coordinate equations, and we get some interesting looking curves that you might never see if you were just playing around with rectangular coordinates. So one of the reasons that polar coordinates are useful or fun or nice to play around with is that graphs of equations in polar coordinates get you some interesting curves that we will see next time in the next section. See you then.